A very good morning to all of you. Hope my AV is okay. Okay, thank you, Saksham. Okay, let us begin today's class. So, in the previous class, we have completed one numerical problem. Today's class, let us see the derivation of transmission loss formula. Already we have seen one derivation formula, that is PL is equal to PG transpose into B into P. Understood? PG transpose into B into PG. So for two plants, for three plants, how to expand this equation, I have explained it. Also, I have taken for two plant example, what is the resultant equation from this that is transmission loss formula. However, all those are approximate. There are several methods are there. So there is one accurate method which is developed by Cron. So that we will be studying it in today's class. Okay, fine. Let us see here. Now this is what I said. This is the accurate method of obtaining general formula for transmission loss as given by Cron. Okay, now let us take one example. So which consisting of only two plants, plant 1, plant 2. Okay, so which is connected to arbitrary number of loads through a transmission network. Understood? So consider a two plant system connected to an arbitrary number of loads through a transmission network. So this is the example, two plants but arbitrary number of loads. So these loads, plants and loads are connected through a transmission network. So here we are going to consider the three cases. One is when only plant 1 is supplying the load current. Other case is when the plant 2 alone is supplying load. The third case will be when both the plants are supplying load. These are the three cases we will be dealing it in today's class. Okay, so that we will see it today. So now we see this is a two generator plant. So this is a figure. So two plants we are having it, plant 1 and plant 2, and it is connected to arbitrary number of loads, load 1, load 2, load 3, etc. through a transmission network. This is your transmission network. Understood? So as I said, there are three cases we will be dealing it. So first, plant 1 alone is supplying the load current ID. Understood? So where plant 2 is not supplying any load current, so that's why we have shown it as open. So this is the case 1 we are seeing it. So under this condition, that means when plant 1 alone is supplying, so in this network there are several lines, several three-phase lines are there. In that one, so let us consider one line, that is one branch as P, and the current through that line or branch is represented by IP1. Understood? So there are several transmission lines are there. So in those transmission line, we are considering one line or one branch which is designated as a branch P, and the current flowing that through that branch P is indicated by IP1. Okay. So this is the example we are considering it. Two plants connected to arbitrary number of loads through a transmission network. When plant 1 is supplying the load current, there are several lines will be there. Consider one line which is considered as a branch. The current through that branch is IP1. Okay. Now under this condition, so as I already told, so the entire load current ID is supplied from plant 1. This plant 2 is open, isn't it? This is the case we are going to deal it. This already I have explained. So therefore, let the current in line P, that is branch P, be IP1. That is also I have explained it. So after considering that term, let us define MP1, let us define some factor MP1 is equal to the ratio of that branch current to the total load current. The ratio of this branch current to the load current. If you are considering the another branch, so P branch. Suppose if you are considering the fourth branch, then it will be I41. So therefore I41 by ID. That's how we have to define a factor MP1. What is this MP1? I will tell you later. So MP1 is equal to ratio of branch current to the load current, total load current. Okay, so this is the thing we are going to define. Similarly, consider this figure where plant 2 alone, you see it here, it is supplying the entire load current ID, where plant 1 is not supplying, so it is kept open. Understood? So this is a case 2. That means only one plant 2 alone is supplying the load current. You see ID is supplied to this load current. Then same thing, let us define a factor, corresponding factor MP2 is equal to the corresponding ratio of branch current to the total load current. Because here it is a plant 2 is supplying, so suffix 2 we are using it, IP2. Okay. So that's how we are taking. Suppose if you have another plant, then this becomes IP3. So IP3 by ID is equal to MP3. Understood? So here I am taking it only two plants example and we are trying to derive it. So we have defined these two factors as a ratio of branch current to, that is the respective branch current to the load, total load current. When plant 1 is supplying, it is IP1 by ID. When plant 2 is supplying, it is IP2 by ID. These MP1 and MP2 are current distribution factors. Understood? So these two are known as current distribution factors. Okay. So that is what I am saying it here. Current is nothing but current distribution factors. Now let us take the values of current distribution factors depends on, that is MP1 and MP2 depends on two factors. One is the impedances of the lines and the second is the interconnection, the type of interconnections. So the second one is, it is their type of interconnection, how these networks are interconnected. Understood? So that is the two factors which decides the current distribution factors, depends on impedance of the line and their interconnection. However, these current distribution factors are independent of your load current ID. This is the one thing. Current distribution factor MP1 and MP2 are independent of the current ID. So with these 3 points, so now let us see the third case when both the plants P1 and P2 are supplying this total load current ID. Understood? So both the plants, now you see both the switches are closed, so both are supplying the total load current ID, IG1. The current supplied by one is IG1 and the corresponding current is IG2. And obviously here this is a one branch we are considering it. Current through this one will be your IP. IP we are going to consider. So when both plants are considering, now here you apply the superposition principle. So of the current line in B. So what is superposition theorem state that one? What superposition indicates? In a linear bilateral network consisting of more than one independent source, so under this condition, the response the response in any branch or line, the response in any branch or line is the algebraic sum of the individual responses caused by the independent sources. Is it clear? So this is the thing, superposition theorem. So in a linear bilateral network consisting of more than one independent source, the response in one line or one branch is the algebraic sum of the responses caused by the independent sources. Understood? So that means what? This is case 3, isn't it? So what is case 3 is when both the plants are supplying. Case 2 is when plant 2 alone is supplying. Case 1 is when plant 1 alone is supplying it. So therefore, so it is equal to the total current in this case is equal to algebraic sum of the response of the algebraic sum of case 1 and case 2. That is your superposition theorem. So applying superposition to theorem, so the total branch current, that is the response in one current, is equal to algebraic sum of this case plus algebraic sum of this case. That is MP1 current distribution factor in the corresponding current IG1, and MP2 is the corresponding response into the corresponding current IG2. So this is by applying superposition theorem to this one. So it is the responses of this is the response due to plant 1 and this is the response due to plant 2. So it is the algebraic sum of both the independent sources, that is equal to total response IP. Hope you understood this one. And MP1, MP2 are your current distribution factors, so which depends on impedance of the lines and their interconnection. Please keep this one in your mind, because this 2 points is required when we are solving numerical problem. So call this as equation 1. Okay, fine. Obviously, I told already IG1 and IG2 are current supplied by plant 1 and plant 2 respectively. Looking into the figure, you can say that one. So nothing special about that one. What are IG1, IG2 are? The currents supplied by plants 1 and plants 2 respectively. And what is IP? Is the total, that is the current that is flowing through the branch P. Understood? So now let us take, at this stage, let us make certain simplification assumptions. We are going to make some simplifying assumptions, because whenever we want to derive any complicated system, so we have to make some simplifying assumptions. So like we have made it in load flow studies for some simplifying assumptions, isn't it? So similarly here also, whenever we are deriving some important relation, so what we have to do, we have to make some simplifying assumptions. So what are those assumptions? The first one is all the load currents will have the same phase angle with respect to a common reference. You remember this one? All the load currents, whether it is ID1, ID2, ID3, etc., whatever it is, all the load currents will have the same phase angle with respect to common reference. So this is the first assumption we are making it. The second assumption is X by R ratio. Any transmission line you take, so it is identified by its X by R ratio. You are studied in transmission and distribution subject. X by R ratio. So X by R ratio of all the transmission lines are assumed to be same. Understood? So this is a second assumption. So before moving on to the second assumption, let us see this first assumption. Audio, okay, very high. You reduce your volume from your end, Saksham. Is it okay now? Okay. Latency, okay, okay. We'll check now. Okay, now is it okay? Audio? I will reduce my latency. Let us check. Still problem continues, please inform me. Okay, so let us see, understand this implication of this assumption. Consider the load current at ith bus. Understood? So that means what? In order to understand this implication, this assumption, all load currents will have same phase angle with respect to a common reference. To understand this implication, so let us consider the load current at ith bus. So at load current at ith bus is IDI. Load current is indicated by ID, but at ith bus it is IDI. So let us take magnitude of that one. Magnitude at an angle, usually in polar form, the current is represented IDI at an angle of delta I minus phi I. Delta I minus phi I. This delta I minus phi I is replaced with theta I. Just we are explaining this assumption. That means we'll have same phase angle with respect to common reference. So let us consider a particular load current at ith bus is given by at an angle delta I minus phi I, or in turn is equal to IDI by at an angle of theta I. Okay. Now what is for this delta I is the phase angle at bus. Understood? So that is delta I is the phase angle of the bus voltage. And what is this phi I is the lagging phase angle of the load. Phi I is the lagging phase angle of the load, and this is the phase angle of the bus voltage. So this is replaced by your theta I. Since delta I, phi I vary only through a narrow range at various buses, that means this delta I and phi I, the variation in these two is not much, so it will vary through a narrow range. So therefore, it is reasonable to assume that theta I is same for all load currents at all times. This is the just to understand, to make you to understand this assumption. So this is the explanation which is required. So theta I variation is very small. So therefore, it is assumed to be same with respect to all the, that means it is same with respect to common reference. Is it clear? So it is reasonable to assume that theta I is same for all load currents at all times with respect to a common reference. So that is the important point, you should keep it in mind. So this is the first assumption, and this is a justification why it is constant. That is why it is phase angle, all load currents will have same phase angle with respect to a common reference. Now second assumption, I said x pi r is same for all the network branches or the network lines. So these two assumptions lead to us the conclusion that IP1, what is IP1? IP1 is a branch current, the response in a branch P, and ID in figure A. Figure A, what is IP1? Is the current in branch P when plant 1 alone is supplying the load current. Figure A, case 1, have the same phase angle. So the IP1 ID will have same phase angle. So therefore, similarly, IP2 and ID will have same phase angle. Understood? So that is the meaning. Suppose if you have IP3 another plant, IP3 and ID will have same phase angle. If you have fourth plant, IP4 and ID will have same phase angle. So these are, with these two assumptions, it is clear that the angle between IP1 and ID and IP2 and ID, if it is IP3 and ID, IP4 and ID, etc., will be same with these two assumptions. So with these two assumptions, we are going to derive the loss formula. So therefore, with these two assumptions, the current distribution factors MP1 and MP2 will become real instead of complex values, because they have same complex angle with these two assumptions. So MP1 and MP2, that is current distribution factors, will become real rather than a complex values. Now let us take the two currents that is contributed by plant 1 and plant 2 in the figure you have seen, Ig1 and Ig2. Let us define Ig1 is equal to magnitude of Ig in polar form. In polar form, Ig1 at an angle of sigma 1. Understood? At an angle of sigma 1. And Ig2 is equal to magnitude of Ig2 at an angle of sigma 2. Let us define the currents of plant 1 and plant 2, that is Ig1 and Ig2 as this one. So where sigma 1 and sigma 2 are the phase angles of Ig1 and Ig2 respectively with respect to a common reference. Understood? So these are the phase angles, sigma 1 and sigma 2 are the phase angles of this Ig1 and Ig2 with respect to a common reference. Now equation 1, what is equation 1? Ip is equal to mp1 into, let me show you that one. This is the equation 1. So Ip is equal to mp1 Ig1 plus mp2 Ig2. So this equation can be written as, now equation 1, you see I am going to write it here like this. Hope you understood this one. The equation 1 is Ip is equal to mp1 into Ig1. What is Ig1 here? Is equal to magnitude of Ig1 at an angle of sigma 1. So this one in rectangular form, this one in rectangular form. How to write? Ig1 cos sigma 1 plus Ig1 sin sigma 1. Is it clear? The same Ig1 in rectangular form plus mp2 into Ig2. What is Ig2 in polar form? So that one I am representing it in rectangular form. So this is the polar form is there, isn't it? So this is, I am representing it in rectangular form. So the whole thing is your Ig2. Ig2 cos sigma 2 plus Ig2 sigma 2. Hope you understood from equation 1. Substituting this one in rectangular form, so you are going to get this one. Now further let us see, let us take cos terms on one side and sin terms on other side. So let us segregate cos terms and sin terms. You see this one, mp1 Ig1 cos sigma 1, mp2 Ig2 cos sigma 2. Understood? Plus Ig1 sin sigma 1, isn't it? mp1, that is mp1 Ig1 sin sigma 1 plus mp2 Ig2 sigma 2. That means I segregated cos terms and sin terms from this equation after substituting Ig1 and Ig2 in equation 1. Okay. Now squaring on both sides, so we are going to get magnitude of Ip whole square is equal to, this is one term, so whole square, and this is another term, sin term whole square. So these are the two cos terms whole square and these are the sin terms whole square. Hope you are following the steps. So these steps, intermediate steps are not there in the textbook, so I am showing it here for your reference. Understood? Now what we have to do next? So this is like your a plus b whole square, isn't it? This is your a plus this is your b. So a plus b whole square, a square plus b square plus 2ab. So expand it. So let us expand it here. You see here, a square, that is mp1 square Ig1 square cos square sigma 1 plus b square, that is mp2 square Ig2 square cos square sigma 2 plus 2 into ab, 2 into this term into this term, 2 into this term is mp1 Ig1 cos sigma 1, mp2 Ig2 cos sigma 2. Just I have written the terms in order. First m's, next I, then cos terms. Similarly, plus this is also a plus b whole square, sin terms. So that also you continue it. You see the whole term plus this is a continuation. It's not equals here. Please remember this one. So these three terms are for this one plus these three terms are for this one. So mp1 square Ig1 square sin square sigma 1. This is b. mp2 square Ig2 square sin square sigma 2 plus 2 into this and this, these terms. Okay. Hope you understood this one. Now what we have to do? Some of the common terms we will take it outside. Now here you see in these terms, actually this is a continuous equation. After this one, it is plus the expansion of this term. Now I am going to take some of the common terms. If you see this term and this term, okay. Now you see this is mp1 square ig1 square. mp1 square ig1 square is a common in these two terms. So if you take common mp1 square ig1 square common, so what is left out here? Sine square sigma 1 cos square sigma 1, isn't it? In these two terms, mp1 square ig1 square, you take it outside. So what is left out within the bracket? Sine square sigma 1 plus cos square sigma 1. So what is the value of these two terms? Is sine square sigma 1 plus cos square sigma 1 is 1. Sine square theta plus cos square theta is 1. So what is left out? mp1 square ig1 square is left out here in this term. Then here you see these terms. That's why I have written one below the other for better understanding here. Otherwise it is a continuous equation. mp2 square ig2 square is common here, isn't it? This one is common. So take it common outside in these two terms. So what is left out inside the bracket? Sine square sigma 2 plus cos square sigma 2. So what is sine square sigma 2 plus cos square sigma 2 is 1. So what is the term, resultant term of these two terms? mp2 square into ig2 square, isn't it? So that's what I am showing it here. See here, this one. For these two terms, it is mp1 square ig1 square because sine square sigma 1 plus cos square sigma 1 is 1. And for these two terms, it is mp2 square ig2 square because sine square sigma 2 plus cos square sigma 2 is 1, plus the addition of these two. 2 mp1, mp2, ig1, ig2 is common here, isn't it? It is common here. See here, this is common here. This is common. 2 mp1, mp2, ig1, ig2, 2 mp1, mp2, ig1, ig2. So if you take these two terms outside as a common, so what will be left out within the bracket? Cos sigma 1 into cos sigma 2 plus sin sigma 1 into sin sigma 2. If you want, you can write it the extra step in between these two. Understood? So when you take these two terms outside, within the bracketed terms, what is left out? Cos sigma 1 into cos sigma 2 plus sin sigma 1 into sin sigma 2. That means this is resembles like cos A cos B plus sin A sin B. So what is cos A cos B plus sin A sin B is cos of A minus B. Cos of A minus B, this entire term. Clear? So that is the term, I have written it here. This one, the whole this one, now this one is nothing but your cos sigma 1 into cos sigma 2 plus sin sigma 1 into sin sigma 2. This resembles like the cos A cos B plus sin A sin B. So that is nothing but your cos of A minus B. So A is sigma 1, B is sigma 2. So sigma 1 minus sigma 2. And left out terms will be your these common things, 2 MP1, MP2, IG1, IG2. That is equation 2. IP square is equal to. Hope you understood this statement. Sorry, this equation till this point. Okay, now let us move on to the next step. Now you know equation 1 and equation 2 here. Understood? Now let us define what is IG1 and IG2. Already we have defined IG1 in polar form, isn't it? So what is that on IG1 in polar form? IG1 at an angle of sigma 1, and IG2 is IG2, magnitude of IG2 at an angle of sigma 2 we have represented. That is the in polar form. But actually, what is the relation? What is the relation for IG1 for plant 1? That is P is equal to, this is a three-phase system, P is equal to root 3 Vi cos phi, isn't it? So that one root 3 Vi cos phi. So in such cases, so what is P is equal to root 3 cross multiply Vi cos phi. From that one, what is I is equal to P by root 3 V cos phi, isn't it? I is equal to P by root 3 V cos phi. So from this relation, the corresponding currents and voltages and angles I have represented. So I is equal to P by root 3 V cos phi. So I means it is IG1 by plant 1. P means it is PG1 for plant 1. Root 3. So plant 1, the corresponding voltage is V1 and corresponding angle is phi 1. That's all I have done it. With that basic formula, power is equal to, real power is equal to root 3 Vi cos phi, isn't it? So this is what we have done it. So from that one, I is equal to P by root 3 V cos phi, and the corresponding things we have done it. Similarly, on the same lines, you write it IG2. Same thing, Pg2 by root 3 V2 cos phi 2. Call this as equation 3. Understood? This is from three-phase power equation. What is IG1, IG2? You are defined. This is equation 3. Now substituting equation 3 into what is 2? Just now we are derived in the last slide. Again, for your convenient purpose, so I have represented here. This is your 2. Understood? So IG1, IG2 is there. So substitute this IG1 and IG2, that is equation 3 in equation 2. That means here IG1, here IG2, replace this one. IG1, IG2, replace this one. So when you substitute that one, so therefore IP square is equal to MP1 square, IG1 square. IG1 square means this whole square. That is PG1 square, root 3 square, V1 square, cos square phi 1. Clear? Hope you understood this one. Plus MP2 square, IG2 square. IG2 square means this square. That is PG2 square, root 3 square, V2 square, cos square phi 2. Plus 2 MP1 MP2 plus 2 MP1 MP2, IG1 into IG2. IG1 is this one and IG2 is this one into cos of sigma 1 minus sigma 2. Call that as equation 4. So hope you are following the steps. I am going slowly here. So substitute equation 3 into IG1 and IG2. So this is the resultant one. You got it. Okay. Now, after doing this one, what is the total transmission loss? Can you tell me what is the total transmission loss? There are different ways, I said, isn't it? So one way is, one simple basic formula is loss transmission, that is loss is equal to I square R loss. In transmission loss, I square R loss will be there, isn't it? So therefore, what is, suppose there are 10 lines are there. Okay, just you take 5 lines are there. What is the loss in line 1? I1 square into R1, isn't it? What is the loss in second line? I2 square into R2. What is the loss in line 3? I3 square into R3, etc. But what is the total transmission loss? You have to add up all these individual line losses. You have to add up, or you have to sum up all these individual losses. That is I1 square R1 plus I2 square R2 plus I3 square R3 plus etc. Clear? So you have to add up. So with that same equation, so I am representing it here. We have to add up, isn't it? So for that purpose only, this summation, I am showing it for various numbers of lines. That is, P is a branch, we have taken it. So therefore, it is I square R. So for P branch, it is IP into RP. For line 1, it is, what is P is equal to 1. For line 5, what is P is equal to 5. Isn't it? So like that, P is varied from 1 to any number of line, total number of lines. But into 3, why it is 3? It is 3-phase system. It is a 3-phase system. For single phase, it is I square R. But if it is a 3-phase system, then it is multiplied with 3. Understood? So 3 I square R for P number of branches. So therefore, P we have to suffix and we have to add to get the total transmission losses. This is equation 5. Hope you understood. This is again, once again from basics. P is equal to I square R. From that equation for 3-phase system, so this is the equation, you got it. Now what is IP square in this equation 5? This is the whole thing, isn't it? So substituting equation 4 in 5, that is replace IP square with this one. So just I am showing it with substituting 4 in 5. Now you see summation P 3 into IP square. See this bracket open and closed. Within this one IP square, the entire thing I have shown it within the red color. That is your equation 4 IP square into RP. Into RP I represented. Hope you understood this one. Understood? So just substitute it. Now what you have to do, let us rearrange these terms. So here PG1 generation is constant, V1 is constant. So only the variable is here MP1 square is constant. Sorry, it is variable because it's a current distribution factor. So from that one and RP, we are writing it, isn't it? We are segregating the terms and call this as equation 6. How you got this one? From this equation only. You see this one? First, let us take only this term. Each term, let us consider it. So only this is the summation of the whole thing. This is the summation holds good for the whole thing. It is not for only this term. Understood? So first let us take only the summation of this term. Sorry. This term. So how we are going to do it? So when you are taking this one, this entire thing is multiplied with one more term RP. So summation of P MP1 square into RP. This term is also multiplied with RP, isn't it? So MP1 square, it is a variable with respect to P because P is within the summation. But PG1, V1 you see here. Here, what is the variable? Variable is P. Wherever P is there, that you include it in within the summation. Without P, take it outside the summation because it will not make any difference. Here in the summation, you are wearing P, number of branches. But without P, so it will not have any effect on this element. That is Pg1 square by root 3 square V1 square cos square phi 1. Now here root 3 square means what? Root 3 square means it is 3. So 3 gets cancelled, isn't it? This is root 3 square means it is 3. Okay. So 3 gets cancelled in this first term. So what is left out? Pg1 square by V1 square cos square phi. So this term doesn't have any P. So this I am taking it outside the summation because the summation limit varies for P. So whatever P suffix is there, that you keep it within the summation. That is MP1 square into RP. Don't forget this RP. So that is the term I am writing it here. Here you see first term. You see, focus on first term. Pg1 square V1 square cos phi 1 square Within the summation, whatever p suffixes are there, that I am keeping it, because here the variable in summation is p, and this term doesn't have any p. So even putting that one within the summation will not do any, will not make any difference. That's why I'm taking it outside. Clear? Now coming back to this one, second term. Second term I'm going to consider. What is the second term? This is the second term. mp2 square pg2 square by this one. So this is the second term into 3 within the summation into rp. So that means what? This is 3 is there. Root 3 square means again 3. 3 gets cancelled in the second term. So what is left out? Pg2 square by V2 square cos square phi 2. I am taking it outside the summation. Within the summation it will be, so summation mp2 square into rp. That is your second term. I am representing it here. So this is the term. Pg2 square by V2 square cos phi 2 square mp2 square rp. Okay. Now coming back to the last term. Hope you are following it. So that's why I'm explaining it slowly here. Last term is this one. So in this term, this whole term is multiplied with the summation of 3 into rp, isn't it? Okay. So here 2 mp1 mp2 is there. So these two terms should come within the summation, and this term no p, this term no p, this term no p. So therefore what you are going to get, pg1 by root 3 into root 3, it will be 3, isn't it? Root 3 into root 3 is 3, and however outside 3 is there, this 3 gets cancelled, isn't it? So what is left out? Pg1 by V1 cos phi 1 into Pg2 by V2 cos phi 2, cos of sigma 1 minus sigma 2, summation of, with p varied from mp1 mp2 into rp, mp1 mp2 into rp, isn't it? So this is what you are going to get here. You see this one, mp1 mp2 into rp. The other terms I have taken it outside the summation. Hope you understood this one. Clear? Call that as equation 6. Now what is the, we have taken this transmission loss formula is also represented, I think let us continue this one in the next class, because I should not be complete this one in a hurry. So till this point, take this Nagarat, that is modern power system analysis by D.P. Kothari. Go through the equation. Some intermediate steps I have shown it in my presentation. However, these are not available in the textbook. So you make some simplifications as per my explanation, so that you will understand the derivation, how he has obtained it. However, I will continue this one in the next class, that is tomorrow's class. So how to obtain the transmission loss formula, how to obtain the accurate transmission loss formula. So I have explained till this point. Please once again revise it, whatever I have explained it. So I will continue this one. Finally, we will say what are the loss coefficients B for this one. So tomorrow I am going to continue with this same loss formula coefficients. Till this point, any doubts if you are having it, you can unmute and you can talk, or otherwise you can put it in a chat box. Any doubts? Don't have any doubts, then I am going to end the class. Okay. Thank you, one and all. Take care. Bye.